we're looking at a review of equilibrium and then looking at the key concepts there. So equilibrium is split into two types, static and dynamic. A static equilibrium is when nothing changes, kind of like when you have in physics, for example, when, for example, there's a weight force pushing down on an object and the normal force pushing up. And because the weight equals the normal force, then it's not moving, net force is zero, and it's a static equilibrium. For our purposes in chemistry, however, a dynamic equilibrium is usually what we come across. And a dynamic equilibrium is when there is constant change at the microscopic level, but there is no change at the macroscopic level. Now, as applied to chemistry, to be able to reach equilibrium, you have two prerequisites. Firstly, you need to have it in a closed system. A closed system is simply a system where energy can move freely in and out of the system, but matter cannot. So think like a beaker with a lid, for example. And you also need a reversible reaction. What do we mean by a reversible reaction? We mean something that's not a complete reaction, so not combustion, but something like the Haber process, for example, which we would represent with a double arrow. So the ideal reversible reaction, of course, is that it will not go to completion. Even though you give it a lot of time, you will still have a non-negligible amount of products as well as reactants. It will not go to completion. It will react, but not to completion. Okay, and those are the prerequisites. But at equilibrium, if a system reaches equilibrium, what can we say? Well, we can most certainly say what we said here on the left, that there is going to be no macroscopic change. In other words, macroscopic properties are constant. And there is microscopic change. And as far as chemistry is concerned, that means the forward weight equals the reverse rate. That's R1 equals R2. And importantly, that's not zero. So if it was zero, it's static, and it's not static. And secondly, macroscopic properties are constant. That includes basically anything you can measure. So think temperature, color, pressure, concentration, volume, and so forth. Okay, so one thing we need to consider is systems at equilibrium and how they react. So examples of system at equilibrium would be, for example, saturated solutions, or for example, when you've got your soft drink in a can, etc. And your chemical reactions. Now, when you've got a system at equilibrium, the point is the conditions that the system is subject to can affect the position of the equilibrium. So you can affect the position, so it can be more reactants or more products. And we rely on Le Chatelier's principle if we're doing it qualitatively, which basically says that the system will react by favoring the reaction that counteracts the change. So the system drives the reaction which counteracts the change. So whenever you have a system at equilibrium, it's already at equilibrium, you make a change. That change will then, the system will then want to counteract that change, and whatever way it can counteract that change, it will then try to counteract it as much as it can. So it will always be partially counteracting it. So if you increase the concentration of a reactant, it will try to decrease the concentration of that reactant. If you decrease the pressure, it will try to increase the pressure. If you, for example, increase the temperature, it will try to decrease the temperature of the surroundings by driving the endothermic reaction. Now, if you are trying to do it quantitatively, then we need to look at the concept of K, which is the equilibrium constant. So the equilibrium constant K is defined to be basically the concentration to the coefficients, the power of the stoichiometric coefficients. So for example, if you have a reaction which is A of capital A plus B of capital B to give you CC plus DD, then this is your equilibrium constant. Keep in mind, of course, that we ignore solids because their concentration is constant, and we typically ignore liquids as well. Okay. There are exceptions to that rule, but generally the concentration changes for gases and solutions. So those are the ones that we would put in for equilibrium constant. So importantly, for any reaction that is reversible, or even if it's not reversible, but usually they'll have equilibrium constants that are not particularly so for your equilibrium constant, you can see it's calculated as the concentration of A. Ooh, let me rephrase. This should be C over D. That's a very common mistake. So it should always be products over reactants. So it should have been the concentration of C to the power of C times the concentration of D to the power of D over the concentration of A to the power of A times the concentration of B to the power of B. In other words, it is the products over the reactants. So for any reaction, reversible or not really, you can calculate a K. And keep in mind that K is concentration of the products over reactants. If you have a complete reaction, then it will basically always go very far to the right. You'll have a lot of C and D and not much A and B. So if you have a complete reaction, the K is very large. If you have no reaction, then K is very small. If you have a sort of K that's sort of in between, and you might think of this as anywhere from say 0.1 to 1,000, but of course it's a sliding scale. So if your K is moderate, then you'll have a reversible reaction. But of course, it's numerical. So the bigger K is, the more complete the reaction is, which means the more towards the product side it gets. And the smaller K is, then the more towards the reactant side it gets. Importantly, K is not only affected by the reaction itself, but K is affected by the reaction, of course. Which reaction are you talking about? The ratios you're using specifically. So for example, if you're using SO2 plus O2 to give you SO3 with a half, like that, gas, 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 versus if you were doing 2SO2 plus O2 to give you 2SO3, then you would get a different K. So pay attention to the actual numbers as well. And then the very important one that we're leading into, of course, is that K is also affected by temperature. So as the Chatelier principle tells you qualitatively, if you change the temperature of the system, then the system will react by pushing the equilibrium towards, if you increase the temperature, it will push it towards trying to lower the temperature. So it'll push it towards the endothermic reaction. So clearly, temperature affects K because you're changing which way it goes. If you think about it in terms of Le Chatelier's principle, then as temperature increases, if it's an endothermic reaction, then K will increase. Of course, if it was exothermic, then K will decrease. We can draw up a table, and give you all sorts of conditions, but you just want to think about it sort of logically, right? When the temperature goes up, by Le Chatelier's principle, an endothermic reaction would be pushed to the right, so K goes up. If temperature goes up, if it's an exothermic reaction, you'll want to push it to the left, so K goes down. Of course, conversely, if temperature goes down, if it's an endothermic reaction, the K will go down. If it's an exothermic reaction, K will go up. Now, one thing quite a few students get confused by is the difference between what's called the reaction quotient and the equilibrium constant. So we often have Q equal what's called the reaction quotient. And for all intents and purposes, you're working out the reaction quotient Q in the same way as you work out K. So it would still be C to the power of C times concentration of D to the power of D, all over concentration of A to the power of A times concentration of B to the power of B. Still the same thing, but importantly, this is at a particular moment in time, for concentrations at a particular moment in time. And it is unknown if the system is at equilibrium. When K is calculated, these are at equilibrium. So once you've decided what we said earlier, what reaction you're talking about, the specific equation you're talking about, and the temperature, once those things are set, then your K is basically set. Okay? So K is your equilibrium constant, which is, by definition, a constant, assuming you are talking about a particular reaction with a particular equation at a particular temperature. And so when the system is at equilibrium, Q must equal K. Now, if Q is not equal to K, then that just means that the system is not at equilibrium. And you just need to remember that Q basically wants to go towards K. So if Q is greater than K, then you can think of it as Q needs to go down to get to K. And if Q needs to go down, that means either the numerator needs to go down or the denominator needs to go up, or both. And therefore, recognizing this as products over reactants again, your products are going down, this is going to go up, and so that means you are going to shift left. Of course, the other is true. If Q is less than K, that means Q is too small. If Q is too small, therefore you want to increase Q. Q needs to go back up to get to equilibrium, and that means the system will shift right. So this is your quantitative method for how to determine which way the system will shift. And we'll be looking at a few questions here shortly, of course. Okay, so those are your key concepts with equilibrium. Now, in addition, you also have the fact that you can apply it to your solubility product. So we have this concept of KSP, which basically is your equilibrium constant. But applied to the solution of ionic compounds. So if we take an ionic compound that we say is insoluble, such as, for example, barium sulfate, we know from our solubility rules that barium sulfate is insoluble. Now, in reality, barium sulfate, like basically everything, is always to some extent soluble. Not by a lot, but it will dissolve a little, and some of it will become barium ions and sulfate ions. So that is what dissolution is about. The dissolution of an ionic compound is when your ionic compound in crystalline lattice form has its ions separated out and hydrolyzed by the water and solvated by the water through the ion dipole attractions, which basically separates the two ions apart. Now, if it was something like sodium chloride, which we assume is very soluble, then we just write it like so. It just completely dissolves and basically none of it precipitate back. If it's saturated, it will precipitate back. But the thing with an insoluble compound is that it reaches saturation very quickly. So we say it like that. Basically, it's insoluble because you've put too much barium sulfate in. Some of it, a very small amount, will dissolve, but that then immediately means that the solution is saturated. Because the solution is now saturated, you've now got a dynamic equilibrium existing between the barium sulfate solid, the precipitate, which is slowly, very slowly dissolving. So this is your R1, into its constituent ions. On the other hand, these ions will then repeatedly meet and recrystallize, that's your R2, into barium sulfate. So here, your KSP would equal the concentration of your products, which would be barium and sulfate. Now, you would divide typically by the concentration of your reactants, but here our reactant is a precipitate and a solid. And so, as we said, we typically ignore those. When we ignore those, because there is a number for the concentration of barium sulfate, we're just not putting it in, then we formally call it the KSP. So in this case, it's the KSP, but it more or less means the same thing as before. And very typically, if your KSP is high, then it's very soluble. If your KSP is low, then it's more insoluble. So the KSP of an ionic compound will then also give you some indication of how soluble that compound is. Great. Does anyone have any questions? Okay. So since no one's got any questions, let's start looking at the actual questions now. So